So now we're gonna see a little bit of the finite element analysis, and specifically this consistent tangent operator, which is nothing but CP, but modified to carry out the numerical solution. So in continuum mechanics, we usually have these kind of problems. Where we have to find the displacement inside a valley, a continuum valley that satisfies elastic equilibrium or elastoplastic equilibrium or static equilibrium in general. So computationally, we cannot solve it for every single point in the continuum, so we have to discretize it. And a very good way, powerful way of doing it is using finite elements. And the name of the game is usually always having equilibrium, right? So the external forces minus the internal forces have to be equal to what? If I want a static equilibrium.
0.
0. Right? And when we discretize or we approximate it, we want to make it 0. So we define this residual that we want it to be 0. Right? And the name of the game is find displacements dm plus 1 in time, right? Such that this residual goes to 0. And given, of course, the displacements at dn at time n. How many of you have taken finite element courses? Okay, so what is this term? Who guesses? What we do in finite elements is a method to discretize, to solve differential equations. It's nothing but that. It's not a structural mechanics method or to solve heat problems. It's a method to solve differential equations. So the internal forces is given by this, right? So internal forces is the integral in the domain omega. This is the domain omega. Right. So this matrix B times sigma integrated in the volume. Where this B comes from the approximation of the displacements, right? We approximate the displacements we approximate epsilon, the strength, like this B matrix times the displacement. And remember that in the continuum world, this epsilon, the strength, is nothing but the symmetric gradient of the displacement. So this is the discrete version of this operator right here. This is the approximation. How this guy? What do we have here? Which external forces do we have? Anyone? Who wants to take that? Traction. So we have to integrate the traction, right, in the boundary of traction. This is this one. Using these shape functions. What else? What? Body forces. So this guy B, right? This might be gravity, right? So plus, we integrated in omega, belongs to the body, not to the boundary, using these same shape functions times B dV. And that's it. So this has to be equal to that, so we reach equilibrium, and this residual is 0.
What letter is that? What letter is that? Why you said find something and plus 1?
D,
D, okay.
displacement, discrete displacement. So in elastostatics, we know that sigma is equal to this, the elastic moduli, or tangent, elastic tangent operator, times the strain, the total strain. But we can like interpolate a strain, so we can write it as a vector, 6 times 1 equal to a matrix, right? 6 times 6 times this guy, B, the displacement. And then we can replace this guy here. Here. So the internal forces at time n plus 1 are the integral over the domain of B transpose C A B to the B n plus 1, right? Where this is the so-called stiffness matrix, right? Stiffness. And finally, we have that the name of the game is that we call K, right? Solve K times D equal to F external for D. However, for nonlinear problems, sigma, as we did here, cannot be directly put in terms of the displacement, right? So what we have to do we have to iterate the residual. So with methods as Newton graphs. Right? And the problem is now find dm plus 1 k plus 1 such that this residual is similar to 0, close to 0. And to do that, we can approximate this residual by using a Taylor expansion, right? So in a Taylor expansion, we go so the residual similar to k plus 1. Similar to the residual at k plus 1, right? Plus, what do we have here? The derivative of the residual with respect to d. Evaluated that. K plus delta d. Where delta d is equal to d n plus 1 k plus 1 minus d n plus 1 k. And this derivative is this stiffness matrix at k. So in the end, what we have is delta d n plus 1 k plus 1 equals to minus k inverse times the residual n plus 1 times at the iteration k. So what we do here is that if we are standing here, before going to the Tm plus 1, we iterate here k times. Till what? We iterate to
less than some.
yeah, r goes to 0, and it's enough 0. I mean, it goes to 0 as close as possible, let's say. So we iterate iterations. So r goes to 0. And then, once this R has converged to the tolerance, we go to the following time step and do the same thing, and they go to the following time step. We don't move from the time step that we are at if we don't have this residual being close enough to 0. questions?
What does the K stand for? That little K up there. What is this superscript?
This is the iteration. It's the K iteration.
Number. Okay.
So this is the K plus 1 iteration. This is the K. I'm computing K plus 1 from the K. I go back.
And N is a time, so to speak.
N is the time.
Okay.
This is the time step.
Right.
And this is the iteration. We fix this one. We're still there. We haven't moved in time. And we iterate within K till converging, till making it very close to 0. So it's very important to compute this stiffness matrix K. So K, as we said before, is the derivative of the residual with respect to D, right? So we call it R prime. But R is this. So it's the derivative of the external forces with respect to D plus the derivative minus the derivative of the internal forces with respect to D. But in general, not always, the external forces do not depend on D. And we find that this K is minus the F internal, well, the derivative of the internal forces, which sometimes is also called F prime. And as we said before, this is the stiffness matrix. And now we know this from the finite element discretization, right? So F prime is equal to the derivative with respect to the displacement of what? This matrix B B transpose sigma d omega. If the domain doesn't depend exactly on the displacements, what we can do? The contour of integration. We can take this integral inside, right? So this is equal to omega dt. Using the chain rule, we can do what is this? What is this?
Elastic modulus tensor.
This is here, right? And this I'm approximating this one. So remember, this is, so this is B. Then you get this C, B. So F prime is equal to the integral of B transpose C B, as we said before. We want to show we will show that C, this C right here, is not equal to the C EP, to the analytical tangent modulus. In general, we want to do this. We want to show that. So we want to motivate that problem. We have here a curve, and the tangent is dy to the x, and we define it to be a function of x. Right? So let dy to the x, which is the tangent to the curve, be a function of x. Hence, we can do that. Okay, integrate. And from that, we get y at k plus 1 is equal to 1 at k plus this integral. K to x k plus 1 x dx. And this is the exact solution. We know this guy, and as far as we integrate it analytically, we get the exact solution. And now we want to compute an approximation using backward Euler. So using backward Euler, we want to compute an approximation y bar at k plus 1. So we expand the Taylor series. Yk plus dy to dx. If we want it to be backward Euler, it should be evaluated at k plus 1 delta x, right? So plus high order terms, but we cut that. So this becomes equal to that. And we can rewrite it as this is f of x, right? Because of that, evaluated at xk plus 1 delta x. What is delta x? Delta x is equal to xk plus 1 minus xk. And now we want to compute the tangent. See. So from the exact, this is the approximation. And remember that this one is exact. So from the exact, we have that d yk plus 1 with respect to d xk plus 1 is equal to, if we derivate this one with respect to xk plus 1, what do we get? This is fixed. The derivative of this integral with respect to xk plus 1, and the integral goes from xk to xk plus 1 is what? F at xk plus 1. And this is C. And now the approximation. Now we have to derivate this one. So it's d y bar k plus 1 with respect to dx k plus 1 is equal. We know that this one is fixed. 2. And then we have to derivate this one. F prime, right? xk plus 1 delta x plus, what's the derivative of this with respect to xk? xk 1 plus f x k plus 1. But this guy here is nothing but the exact solution, right? It's nothing but C. So the approximation is the exact plus some contribution f prime x k plus 1 delta x. Some algorithmic contribution. See, it's not the same. Approximation has a contribution. coming from the discretization. And this algorithmic contribution is of the order delta x. Right? So this is the order delta x, which means that it converges slowly. It's linear. And that's why, in general, the CTO is not going to be equal to the analytical tangent. Questions? So now we want to do that for the J2 model. But for the whole convol, isotropic kinematic hardening. So sigma prime is equal to C times the elastic strain rate. Now we can express it in terms of the flow rule, right? So this is equal to what? Lambda dot. And for this particular model, what comes next is n. Right? So we can do this minus C, or let's say lambda dot C plus double contracted with n hat. What is this? 2 mu. That's a pretty sharp right now. So we get two mu lambda dot n, right? But lambda dot in the analytical model is equal to what? Is a little bit harder. 2 mu plus h over mu plus h 2 mu. And here we have n hat double contracted with epsilon dot. Now substituting this one here, we have right? Which gives us a sigma dot equal to C elastic minus 4 mu squared divided by 2 mu plus h n hat times n hat, everything double contracted with epsilon double. Let's check. Yeah, exactly. And this is what? This is the continuum CEP, right? That's it. That's the continuum tangent operator. And now we want to derive the algorithmic tangent operator, or the consistent tangent operator. So for that one, so consistent for that one, we know that sigma at n plus 1 is equals to sigma at n plus 1 trial minus 2 mu delta lambda n hat at n plus 1. Where sigma n plus 1 trial is equal to
sigma n plus
delta epsilon. Is that correct? Is that true?
plus sigma n
plus C.
Plus sigma. Oh, yeah, plus sigma n. Plus sigma n. Plus sigma n. Right. And delta epsilon is equal to epsilon at n plus 1 minus epsilon at n. Now we want to compute this CTO, which is the derivative of sigma at n plus 1 with respect to epsilon at n plus 1. So it's the derivative of sigma n plus 1 trial with respect to epsilon at n plus 1 minus 2 mu, the derivative of delta lambda times n at n plus 1 plus delta lambda times the derivative of n hat at n plus 1 with respect to epsilon at n plus 1. Is that right? What's this? Here we have sigma n plus 1 trial. We're deriving with respect to epsilon n plus 1. This is fixed. We know it. And then we have this. But delta epsilon is this. So what's this?
C.
So C. And then we have that C equal to CE minus 2 mu derivative of delta lambda with respect to epsilon n plus 1 plus delta lambda and now we have to compute these two derivatives. And that's it. Simple enough. So let's do the first one. Who tells me this one? Delta lambda is equal to what is up here?
Fn plus 1 trial.
So we're doing the combo, right? So C trial at n plus 1 minus
Kappa n.
kappa at n. So the derivative of delta lambda with respect to epsilon at n plus 1 is, this is fixed, we already know it. This is a constant, it's also fixed. 2 mu plus h, derivative of this norm. And now we can do it by once again using the chain rule. So we do this guy with respect to sigma n plus 1 trial times sigma n plus 1 trial with respect to epsilon s n plus 1. And we know this. What is this? Just computed that one. C. So this CT. And we are left to compute this permutation. And we can use the chain rule once again and do this guy with respect to C itself. I will contract it with the sigma of C m plus 1 trial with respect to the sigma m plus 1. What is this? This what? This derivative here. Is the norm of something with respect to that something. In this case. Have, right. Twice. What is it? This is 1 and this. What do we get here?
Over this one.
What's this? N half. This guy is N half. So this one here is N half. Now we have to compute this one. We can express it as, what is this?
S minus alpha.
S m plus 1 trial minus alpha at the end, right? But we know that alpha then doesn't depend on sigma n plus 1 trial. So this is equal to and this one is easy. We can express that one what is this in terms of this is equal to sigma n plus 1 trial minus minus the pressure times the identity, right? But the pressure is the trace divided by 3, and the trace is sigma m plus 1 trial double contracted with the trace. The identity. This is the trace, this is P, times the identity. And this gives us this forwarded symmetric identity minus 1/3 second order identity times second order identity. And it had a name. We gave it a name class a couple of weeks ago. This is called the deviatoric. This is the deviatoric projection. What is it? Here?
Yeah.
Oh, yeah, it does again. Well, in any case, if it is a diet, it is not. Because this is an scalar. Now, let's put things together. So this is this guy here. And this guy here goes here. So we have, and this is this guy here. Is equal to n hat times the deviatoric projection, right? And this guy here comes over here. And then we can say that the derivative delta lambda with respect to epsilon n plus 1 is,
Question.
yes,
Should that be n sub n plus 1?
which one?
The first line.
This?
No, above.
This?
Yeah.
Yeah, if I forget, just so many things. So this derivative here is that one plus CE. That one, I mean this one. Times CE. And the result has to be that. What is this? It has to be 2 mu n. So I get 2 mu, 2 mu plus h times m diet n. This is the first derivative that we needed. Right. We're done with this.
Should there be double contract? The one between those two games?
Here?
Uh-huh.
No. Oh. This gives you no. Oh, maybe. Let me check. And vector projections. Oh yeah, this is only n. Yeah, I don't know what happened. Oh yeah, because this, I have to contract this with this, right? And this is what? This contraction.
Just n.
It's just n, right? And then I have to contract this with that, which is 2 mu n. This is 2 mu n. That's how it works. Let's do the final one, which is this derivative right here. The n hat n plus 1 with respect to epsilon at -1. So we can express n hat as this, right? And then I can use the chain rule to do this with respect to sigma n plus 1 trial. And then sigma n plus 1 trial with respect to epsilon at n plus 1. Once again, what's this? CE. And then I have to compute this. Gives me something like that. We already know this one here. Choose it. What is this? Just finished doing that. This.
Yeah.
What?
Over there.
What?
And double contract with that.
This one?
Oh no, it's not that.
Just P.
This is the elementary project. This one, that one. All of them. So if I contract this with this, what do I get? This double contracted with this.
Itself.
This, because it is already elevated. Right? And so, wrapping things up, we end up with this being equal to 2 mu you know this is m plus 1. Now, this is the second result that we were looking for. So we can write C, the CTO, which is
Sorry, what happened to the cube term?
oh, right. So this double contracted with this is this one, right? And this double contracted with this is this one. So you add is to C, right? So and you have that goes with that, and then you have this. You have C diet C. So C over one of them is N, and the other C over the other one of them is N. So you get N times N. And you're left with only one norm that appears here. That's one. Is that clear for everyone? Well, let's keep going. That's it.
Why did we draw the C in?
This? Why is this that?
No, where does it go in what
It's
follows?
2 mu.
Oh, then it, right. So here we have this 2 mu, right? It comes from these operations here. Then we have to double contract this whole thing with C, right?
Ah, okay.
To get this derivative.
Right.
So the moment that you contract one of those n's, you get 2 mu n. And you end up with this 2 mu up here. Right?
Okay.
All right. So this is the CTO. This is the consistent tangent operator. And if you guys take a look to your notes, what is this?
See.
This is CEP. The continuum, the exact one. And this part here is the algorithmic contribution of order what? Delta lambda. Of order delta lambda. Same one, linear, slow. That's it for today.